What do IIR filter pole zero plots mean for electrical engineers? Have you ever wondered how electrical engineers design filters that shape signals? One key tool they use is the pole zero plot. Let's break down what this means, especially in the context of infinite impulse response filter design, signal processing, and digital signal processing. First, let's clarify what a pole zero plot is. This graphical representation shows the locations of poles and zeros of a filter's transfer function in the complex plane, specifically the z-plane for discrete time systems. The transfer function itself is a ratio of two polynomials in the complex variable. The roots of the numerator polynomial are known as zeros, while the roots of the denominator polynomial are called poles. In a pole zero plot, zeros are represented as circles and indicate frequencies where the filter output is zero. On the other hand, poles are marked as crosses and indicate frequencies where the filter's response magnitude tends to infinity. Now, the placement of these poles and zeros is not just for show. It has real implications for the filter's behavior. For instance, stability is a primary concern. For an infinite impulse response filter to be stable, all poles must lie strictly inside the unit circle in the z-plane. If any poles are on or outside the unit circle, the filter may become unstable, leading to outputs that grow without bound or oscillate indefinitely. While zeros do not affect stability, they do influence the shape of the frequency response. Speaking of frequency response, the unit circle in the z-plane corresponds to frequencies ranging from 0 to the Nyquist frequency. The proximity of poles and zeros to this unit circle directly affects the filter's gain and phase at those frequencies. Poles that are close to the unit circle can create peaks in the frequency response, while zeros near the unit circle can cause dips. The arrangement of poles and zeros also helps identify the type of filter being designed. For example, if poles are clustered near the zero frequency, it suggests a low-pass filter. Conversely, if zeros are near the zero frequency, it indicates attenuation at that frequency. Additionally, the impulse response of infinite impulse response filters is theoretically infinite due to the poles being inside the unit circle. The location of these poles also determines how quickly the impulse response decays. From a practical standpoint, pole zero plots are essential for electrical engineers. They allow for the design and analysis of filters by visualizing how changes in pole zero locations affect stability and frequency response. Engineers can diagnose issues like instability or unwanted frequency behavior without needing to compute the entire frequency response explicitly. In applications such as control systems, communications, and audio processing, understanding pole zero plots helps engineers implement filters that meet specific performance criteria. By using these plots, they can ensure that their filters are stable and function as intended across the frequency spectrum. So, the next time you hear about infinite impulse response filter design, remember that pole zero plots are not just technical drawings. They are powerful tools that help engineers create effective signal processing solutions.